Dear students, today we are going to discuss the properties of indefinite integral. From previous two video lectures, we are discussing, the indefinite integral, how to find indefinite integral by, using the definition of this indefinite integral. Now, the property first is to prove the process of differentiation and inverse are inverse to each other in the sense this, that is d by dx of integral fx dx equals to f of x. This means that when we operate firstly integral to a function and then we operate again the differential, then we get the same function. This means that they are inverses to each other in this sense. Similarly, if we operate differential firstly to a function, then we'll operate this integral, then we will get the function with some constant c. In this way they are inverses to each other. We will prove this. Let fx be the function, capital Fx be a function, and its derivative is f of x, small f of x, then that is d by dx of f of x is small f of x. Taking, which implies by definition of indefinite integral, antiderivative of this small f, that is integral fx dx equals to fx plus c. So this is by the definition of indefinite integral. Now from differentiate this very equation, that's d by dx of integral fx dx equals to d by dx of f of x plus d by dx of c. C is constant, its derivative is 0, that is why I write here 0, simply 0. And by this, by definition, or by defining this f, we define d by dx of capital Fx equals to small fx, so simply it is f of x. Hence we proved this very, that is when we operate integral to a function and then again operate in this differential to a function, we get the same function, that is they are inverses to each other. Now we can also use here the inverse of two function, concept of inverse of a function, because inverse means when g or f of any two functions equals to identity function, then we say that g and f are inverses to each other. Here, if composition of dx, d by dx, that is differential and integral, is from one side, it is f of x, that is why they are inverses to each other. Similarly, we can prove the second one, that's integral f dash of x dx equals to fx plus c. We can prove it by using f dash of x equals to d by dx of d by dx of f of x, which implies that integral of f dash of x dx equals to the integral of this very quantity. The integral of this very quantity is simply fx plus c. Fx plus c. You can check this by using the concept of definition of this indefinite integral. So this means that integral of f dash of dx equals to f of x plus c. So this is the property first. Now the property second, if the derivatives of two indefinite integrals are same, if the derivatives of two indefinite integrals are same, then the families represented by these two indefinite integrals are equivalent, or simply we can say that they are equal. Let f and g be two functions, then we know that by definition integral of gx dx is the the family represented by this indefinite integral, or simply the indefinite integral of this, and integral g fx dx is the indefinite integral of this f of x. So they are two families. We have to prove that those are equal. It is given that the derivatives of those two families are equal, which implies that d by dx of integral fx dx equals to d by dx of integral gx dx. Now shifting these two on same side, we get d by dx of integral fx minus integral gx dx equals to 0. Now you know that derivative of constant is 0, or if derivative of any function is 0, implies that function is constant. This means that here the function integral fx dx minus integral gx dx is constant, that is integral fx dx minus integral gx dx equals to c. Here this is one family of curves, this is another family of curves, so their difference is c, and and we simply say that two curves are equivalent to each other if the difference of these two curves is constant. Here difference of these two curves is constant, which implies that the curves represented by the indefinite integral of two indefinite integrals, that is f and g, they are equivalent. Hence in this way we say that two families are equivalent or simply the equal. Now the third property is algebra. Prove that the integral of sum equals to the sum of integrals, or integral of difference equals to difference of two integrals. Now by property first, we know that d by dx of integral fx gx dx equals to fx dx. It is by property first. And d by dx of integral fx dx plus integral gx dx equals to differential d by dx of fx dx plus d by dx of integral gx dx, because differential of sum equals to sum of differentials. That is, here I use that very concept. Here it is this sum function, it is this. Now again by property first, d by dx of integral fx dx equal fx, and d by dx of integral gx equals to g of x. So it is fx plus gx, it is fx plus gx, which implies that d by dx of fx plus gx dx equals to d by dx of fx plus from these two, that is from first d by dx of integral fx gx and d by dx of integral fx plus integral gx, both are equal, which implies that those two are actually equal. Now when two differentials of two functions are from above, differentials of two are equal, which implies that they are equivalent curves, which implies that integral fx gx plus integral fx plus gx equals to integral of fx plus integral of g of x. Actually it is plus c. In difference in integration, there is always one constant, that is constant of integration. That is why we omit here that c, and we simply say that integral fx plus gx equals to integral fx plus integral g of x. Usually this result is true for when functions are finite. If functions are infinite, then we cannot say this in general. That is for infinite systems, that integral of sum of infinite numbers or infinite functions equals to integral of individual sum of the integrals. So this is only true when we consider the finite functions, like if we consider n functions, or if we consider the two functions. But if we consider arbitrarily infinite functions, then it is not always true. Now the third property is for any k real number, integral k f of x equals to k integral f of x dx. That is, we can take a constant out from this integral sign. By property first, d by dx of integral k fx dx equals to k f of x dx, and also integral d by dx of k integral f of x dx equals to k d by dx of integral fx dx. Because k is constant, we can take k out from the differential, and this very here d by dx of integral fx dx equals to simply f of x. By property first, from first and second, this integral k of fx dx equals to k f of x d of x. Now this is the extension of this property third, which is integral f1x plus f2x plus so on to fnx dx equals to integral f1x dx plus integral f2x dx plus so on to integral fnx dx. Or similarly, we can generalize this property fourth for any k as k into f1x plus f2x plus fnx dx equals to k into integral f1x plus dx plus k f2x dx plus so on to k integral fnx dnx. So these were the properties of indefinite integral. We will use these properties while finding the indefinite integral. Inshallah, from in tomorrow's video lecture we will discuss this concept, that is how to find the indefinite integral of any function by using this definition concept. So thank you.